So we are taking here, so A, B, C, D, A plus C and B plus D. A, so A for A comma B and C comma D, AC minus BD, AC minus BD and BD plus BC we are taking here. For all we are taking this value x1 0 and x2 0. So x1 plus x2. So in the addition we are taking here x1 plus x2 comma 0. So in the multiplication x1 0 and x2 0, we are x1 and x1 into x2. But the value is outside is 0, x1 and x2 is 0. But the symbol of I respects of the 0 and comma belongs to C we are taking here. So x plus I, that's the real and imaginary part what we have taken here. X0 plus 0 comma 1. So that is the x comma 0 real part and the imaginary part we are taking here. So 0 comma y we are taking here into y0. So therefore we are writing x comma 0 plus 0 comma y. So we are multiplying here. So x comma y. Why? Because I am adding x plus 0 and 0 plus y. In the addition of the part of x plus 0 and 0 plus y. So x comma y we are taking here. So we can take that, fully observe that here. Fully observe that here. I square is equal to 0 comma 1 into 0 comma 1 we are taking here. So 0 comma 1 into 0 comma 1 multiplying here, therefore the values is 0. But the real and imaginary part what we are taking here, there's a minus 1 comma 0. So with the identified we are taking here, minus 1 we are taking here. So the real and imaginary part, what is the imaginary part and the real part? I square is equal to minus 1. So in the I square is equal to minus 1, therefore I we are writing is equal to minus 1. So the condition of 0 into 1 and 0 into 1, that is minus 1 comma 0. You may notice that x plus yi or x plus iy, yi or iy, that is I is representing the imaginary part. X is the in front of x value representing the real part. So therefore z is equal to x plus y, z is equal to x0 plus 0 1, it is in the y0. In the normal algebra rules we are taking here. For example, we are taking here for example, a plus ib plus c plus id. Both are two different values here. A plus b1. Then we are taking the real parts is I am separating here. A plus c is separating the a plus c is a is real part, c is separate part, and I is the imaginary part of both of them b plus c. So we are writing a plus ib into c plus id. So in the above one is I am taking the multiple ac minus bd plus I into IED plus BC. I already told you there is a different part in addition and multiplication. There is a different parts we are taking here. Addition is the separate real part to real part addition, and the imaginary part to imaginary part addition. But in the multiplication part, A into C the real part, B into D is the multiplication part. But B into D, I square is equal to minus 1. So I square means minus 1 means this side should be called as minus 1. So therefore AC minus BD. Then A into D multiplication, A into D, that is imaginary part. I have taken the I common AB plus B. So C we are taking here. Therefore, so this one another definition in the complex number. Another definition in the complex number, x plus y is the real number, x is called the real part of x plus iy, and the real number y is called the imaginary part of x plus iy. So x plus iy is the real part and the imaginary part of the complex number. The 0 is often called a real number we are taking here. Usually when we w user that the complex number we are taking here. So in the next one, what we are taking here, w and z are complex number. We mean w is equal to z, and the real part w is equal to real part z, and the imaginary part w is equal to imaginary part of z. So in the process is usually refer the imaginary parts of the complex numbers. So you know that I square is equal to minus 1 and I is equal to minus 1. So we are taking here. So z square plus 1 is equal to 0, which is really the equation x comma y into x comma y plus 1 comma 0, that is equal to, we are multiplying these values, that is 1 0 0. So in the root of c, but in fact for each in c, z square plus 1 is equal to z plus I into z minus I. So moreover, you and z and w are complex numbers. So z square plus w square is equal to z plus I w into z into I minus w, we are writing. All the familiar arithmetic properties of R carry over the C theorems in the sense of that can prove from the properties of R in the list of Z, Z1, Z2, Z3, Z4 or any elements in these complex numbers. What is the properties? You know the properties of alternatives law. What is alternatives law? We're taking here Z1 plus Z2 plus Z3. So here we are taking Z1 plus Z2 plus Z3. We are taking in associative property Z1, Z2 plus Z3, then Z1. Z1 plus Z2 and Z3 we are taking here. So the existence of associative law, then existence of additive identity. Additive identity also defined as there is a C, there is a 0 belongs to C, and Z plus 0 is equal to 0 plus Z is equal to Z. So existence of the additive inverse here. So existence of the additive inverse means minus should be plus, plus should be minus. So therefore minus Z belongs to C. We are writing here Z plus minus Z is equal to minus Z plus Z is equal to 0. We are writing here. Then commutative law for addition we are taking here. In commutative law we are taking here Z1 plus Z2 is equal to Z. And what we are commutative law? Exactly, but Z1 plus Z2 or 2 plus 3 is equal to 5 or 3 plus 2 is equal to 5 or 2 into 3 is equal to 6 or 3 into 2 is equal to 6. In addition and multiplication both should be the same, but in subtraction should be difference, but only commutative Z1 plus Z2 plus 1 in the addition property we are writing here. Associative law in multiplication, associative law in multiplication, associative line multiplication, Z1 into Z2 into Z3 is equal to Z1 into Z2 into Z3. So see here, this is also same from the multiplication part. So existence of multiplicative identity, existence of multiplicative identity denoted by 1. So therefore that is 1 belongs to C, such that Z into 1 is equal to 1 into Z is equal to Z. We are at existence of multiplicative inverse of non-zero elements also we are taking here, that is Z is equal to 0, not equal to 0. So Z into Z inverse, you know that Z into Z means 1 by Z. Suppose Z inverse Z, and that means is equal to 1 we are taking here. There is a non-zero inverse we are taking here. Commutative law for multiplication, we are also taking Z1 into Z2 is equal to Z2 into Z1 also we are taking here. Distributive law also I am getting here. Distributive law, Z1 into Z2 plus Z3. So see here, Z1 into Z2 plus Z1 into Z3 we are writing here. So we check some of the above properties. So some of the additive property 0 is 0 comma 0 plus 0 plus I0 we are writing here. So therefore 0 plus Z, 0 plus I0, x plus iy, see here x plus iy. So therefore 0 plus x plus I into 0 plus y we are taking here. So therefore that is we are writing here x plus iy we are writing the same here. So x plus iy is equal to z. So similarly z plus 0 is equal to z. Similarly z plus 0 is equal to z we are writing here. So the additive inverse of z is equal to x plus iy is that is additive inverse means minus negative. Therefore, I of minus y, which is can be written as minus x minus iy or minus z. All with the real numbers, we can define the difference of the complex numbers. A plus ib minus c plus id. So therefore, write a plus ib plus minus c minus id. So we can writing here a minus c plus I into b minus d. We are writing these one. A plus C and B minus C. D, we are writing this one. Okay. So therefore, A minus C plus B plus ID. So therefore, we are writing this one. So as per the additive inverse, we are taking here. Some one here, some another one we are taking here. Some other one taking here. So W1 minus W2 is equal to W1 plus minus W2, where W1 is equal to A plus IB. So W2 is equal to C plus ID, we are taking here. So the multiplicative defined, the multiplicative identify one is 1 comma 0 is equal to 1 plus 0 into y. So for I into z, so therefore we are taking here, for 1 into z is equal to, and z is equal to 1 plus 0 into y, so into x plus iy. So this is 0, this is automatically 0, so therefore we can write here x plus iy is equal to, we know that real imaginary part, that is z. So z into 1 is equal to z. So let z not equal, to 0. Let z not equal to 0. Let z not equal to 0, then the either x not equal to 0 or y not equal to 0. So therefore x square plus y square not equal to 0 also you can write here. Now the multiplication inverse, z inverse of z is given by, we are taking here z inverse is equal to x by x square plus y square, then y by x square plus y square. So what I am taking here, so one of the problem we are taking here z into z inverse. What am I taking z inverse? We are writing here. What is z? We know that z is equal to x plus iy. We know that. Then what is z inverse? X by x square plus y square minus iy by x square plus y square minus x square plus y square. We are taking here. So therefore, we are taking here. We are taking here x square, x into x. Student, x into x square plus y square by denominator. Then y, iy into iy. అంటే ఏమవుతుంది అంటే I square means minus 1. So I into y, minus 1, minus into minus, plus, plus into plus, plus y square by x square plus y square. This is the first one. Then imaginary part, real part is over. Then imaginary part. What is the imaginary part? X into y by x square plus y square. Then minus, again minus, there is no one. So therefore, again then one, xy by x square, y, this one, x into y, then x into y. I'm taking this one. So therefore, see here, what we have doing here. This one, x by xy, both are cancel, 0 into y. So this is x square by 2, x square plus y square plus x square plus y square. So this is, we are taking the LCM, we are taking this one, x square plus y square. In the numerator also, but plus I into 0, this is 1. So 1 plus I0, 1 plus I0, that is equal to I0, 0. You can write one. So in the multiply, the real part we have to do it. Again, immediately we have to do imaginary part also we are taking here. So similarly, z inverse z is equal to 1. So this is the property of the this one. We have to prove this one. Again, one definition we have to learn here. A non-empty set. A non-empty set with the two binary operations. Called addition and multiplication is a field of the properties that is are satisfied. What the properties we have to satisfy? That one, z1 into z2 or z1 z2 or z1 into z2. Second property, that the useful of the property, that is 0 is unique. Then wz equal to 0 and if and only if that the real numbers is mentioned in the case of the real numbers. The real numbers may be given in ordering less than which are amongst the properties following. Therefore, x not equal to 0, either x greater than 0 or minus x greater than 0, or not both we are taking here. Xy greater than 0, then xy greater than 0, comma, x plus y greater than 0. This is the first condition. This is the second condition we are taking here. So no such ordering can be defined in the complex numbers. So the since I not equal to 0 follows that I greater than 0, minus I greater than 0, So minus 1 is equal to I into I greater than 0. So 1 minus 1 into minus I greater than 0 we are taking here. At the same time 1 minus 1 square greater than 0, but then the both 1 and minus 1 are greater than 0. So contrary to 1 in the before not possible to the inequalities analogs to the reals when discussing the complex numbers, or inequality of accused by involve the real numbers. So epsilon greater than 0 automatically implies epsilon is a real number. So this is the one of the properties of this one. Then we have to discuss about the complex plane. Complex plane. So in the complex plane, there is a natural geometric representation of the complex numbers as a plane. So allows that the real as a line. So this section we shall develop the corresponding between C and R. Corresponding this one, here, corresponding this one. So we are taking the values of C into R into R. So obtaining the geometric representation of the elements of the C, the complex numbers and operations in C. We shall define the polar form of the complex number and modules of the argument of the complex number. We shall see that the every non-zero complex number exactly n or nth root of the in the complex numbers, that is we are writing in C. We are writing in the C, we are taking here. So therefore, we have seen in the previous section, complex number system obtained by defining arithmetic operations in the set R into R. We are also known the elements of R into R. It is therefore reasonable to ask that the geometric insight can be obtained by recording the complex numbers as point of the plane. One obvious way representation of the complex numbers, the rectangular Cartesian coordinates x plus I y represented by the point of the coordination. So in the point of the coordinations are we are taking x and y. Thus the point of the P represent the complex numbers we are taking here. Complex numbers we are taking here. R into R in the plane. Therefore, reasonable geometric insight can be obtained regarding complex numbers as points in the plane we are taking here. Then one obvious representation of the complex numbers to use rectangular Cartesian coordinates. X plus I y represents the both point with the coordinates x and y. The point P represents the what's the point we are taking? P is a complex number in Z, so it is x coordinate. So therefore, Z and its y coordinates we are writing it's an imaginary part of Z. So the x-axis is horizontal is called the real axis, and the y-axis vertical is called the imaginary part. So x is a real part and y is imaginary part. We are taking this one. Then the plane itself is called as the complex plane. Geometric representation of addition and multiplication. So we know that the Z1 is equal to x1 plus iy1. So Z2 is equal to x2 plus iy2. So you can associate the points of PQ with the coordinates of x1, y1 and x2, y2. So with respectively x, y with the plane. 0 is origin. Complete the parallelogram with OP and OQ. The adjacent sides, so are other vertex of the parallelogram we are writing here. So one diagram we are taking here. See the diagram. This is the diagram. X, O, Y. This is 1. This is R. This is a curve here. This is a P of the curve. This one curve is a P. This is a 1. And also, this is a Q. This is a point here. So this is the form vector algebra which is already defined familiar. OP, see here, this is OP. This is OP plus OQ. Which is OP plus OQ. This is 1. This is OR. Okay, these two lines are OP plus OQ. We can OP plus OQ that is equal to OR. So you can also know the elementary coordinate of the geometry x1 plus x2 and y1 plus y2 we are writing here, or the respective xy coordinates are represent the complex numbers x1 plus x2. So see here, x1 plus x2 and y1 plus y2 we are taking here. So therefore, then we are taking here x1 plus y, or the respective x and y coordinates are. So a complex number we are writing here x1 plus x2 plus I into y1 plus y2. Therefore, I think x1 plus iy1, then x2 plus iy2 we are writing here. That is z1 plus z2. So we are writing x1 plus iy1 plus x2 plus iy2, we are writing z1 plus z2. Thus, the data representation z1 plus z2 we are taking here. So therefore, we have to simplify for a fourth vertex of the parallelogram from the OPQ we are taking here. Z1 and Z2 respectively. Hence, the addition of the complex numbers can be visualized as vector addition. So, therefore, another diagram is taken here. This is theta, Z1, X. So, then it most natural associates with the Z1, the popular coordinates or the popular the coordinate R here. So Q of P, where R is the distance, OP and theta is the angle XOP. However, there is the undesirable factor, the above association, which is not present the x comma y coordinate system. Given R and theta, they get unique point with R and theta as polar coordinates. But given the point with throw is uniquely known, this total is known uniquely we are taking here. Then we are writing with one R theta minus 4 pi. The general form of R theta plus R minus 2 pi n pi we are writing here. So n is equal to 0, 1, 2, and so on. This is the most associated step not to be given. So let z is equal to x plus I by be non-zero complex number. So in the form of R into cos theta plus I sin theta. Then R is equal to under root of x square plus y square. Sin theta is equal to y by R. Cos theta is equal to x by R. So therefore, what is the values adjacent by what is the values taken here. The first number R is called as modulus of Z is called argument of Z. So Z by modulus of Z also we can write here R is equal modulus of Z is equal to x plus I by we are taking here. One diagram we can take. Of x comma y. When z is equal to 0, we define modulus of z is equal to 0. So, but we do not define it meant an argument of 0. Non-zero complex number z is written in the form of r into cos theta plus I sin theta. Cos theta plus I sin theta, we say that z is in the polar form. So given any non-zero complex number, argument can be element from a whole real numbers. So 1 plus I can be any element of, we can write here pi by 4, 9 pi by 4, minus 7 pi by 4, 17 pi by 4, so minus 15 by pi by 4. So there is a arguments in the interval of minus pi to pi. 9, 7, 17, 15, you can write these values of this from the above graphical method. Another definition we will take here. If theta is an argument z and theta belongs to minus pi to pi, we call theta is the principal value of the argument of z, and we write it as argument of z. So see here minus pi to pi, the argument of z, we can write this one. So argument of 1 plus I is equal to pi by 4. So we can also 0, 2 pi or 0, 2 pi or minus pi comma pi for. So this is minus pi comma pi, close bracket and open bracket for argument of z. So in this addition and subtraction of complex numbers, in addition and subtraction of the complex numbers given in the polar form, so it is not a present of r. So we can write in the polar form, we are writing here z is equal to r into cos theta plus I sin theta. Then W is equal rho into cos phi plus I sin phi. We are writing here. So then we are taking here ZW rho cos theta plus cos theta cos phi minus sin theta sin phi. The cos A minus cos the formula cos A cos B minus sin A cos A cos B minus sin B is the formula of this one. So therefore plus I into cos theta plus cos theta sin phi plus sin theta cos phi. Cos A cos A plus B cos A minus B sin A plus B sin A minus B formulas using in this one. So cos I'm taking theta plus 5 plus I of sine theta plus 5 we are taking here. Modulus of ZW is equal to R into rho of modulus of Z. So we can argument of ZW can be obtained just by adding arguments of Z and W. If you want to work with the principal values, the majority of difficulty even if theta and phi are in minus 5 comma 5. So we had theta and phi, we get the answer outside of the interval minus 5 comma 5. So if you want to work with the principal values, you have to make sure to get the answer back into minus 5 comma 5. That is the argument, Z plus argument. We have to add subtract 2 pi to obtain argument of Z into W. So Z into Z inverse, we know that 1. So Z not equal to 0. Z into Z inverse, we know that Z into Z inverse is equal to 1. So Z not equal to 0. We know that we define W defined by Z. So W into Z inverse is equal to W Z inverse. If you have to write this the same value. So now we have to, just one, we have to verify the same here. Then argument of 1 by Z is equal to argument of Z is equal to 5. So therefore, Z is a negative real number. Argument of 1 by Z is equal to minus argument of Z. So Z is not a negative real number. So Z is not a negative real number. So that Z is not a negative real number. Why? Because it is modulus we are writing 1 by Z into 1 by Z we are writing here. So nth roots of a complex number. Roots of a complex number. Nth roots of a complex number we are taking here. Writing the complex number in a polar form, very useful to solving the equation in the form of z power n is equal to a. So a is a given non-zero complex number and n is a positive integer. So therefore modulus of z is equal to modulus of z of n. So theta is argument and n theta is an argument of zn we are writing here. One definition we have to take here. Definition. The solution of z power nj are called nth roots of E not equal to Z. So Z power n is called. So where we write A is equal to cos phi plus I sin phi and Z is equal to R cos theta plus I sin theta. Already I told this one. Already so I already this one. Just a minute. cos theta plus I sin phi. Z is equal to r cos theta. Z is equal to r cos. Z is equal to r cos theta plus I sin theta. Cos theta plus I sin theta we are writing. Zn is a. We are writing here r in r for n. Cos into n theta plus I sin n theta. So therefore rho into cos phi plus I sin phi we are writing here. So therefore, there is a simplification r in cos n theta is a simplification we are writing. This is cos n theta plus sin theta. Therefore, that is rho cos phi and r power n sin n theta. That is rho sin theta we are writing here. So therefore, sin n theta is equal to sin phi. The equation of the certainly fulfilled by r power n is equal to p and n theta is equal to phi. R is equal to n root p we are writing here. So theta is equal to phi by n. So n and the root of p we are writing here. Denote the positive nth root of positive real number p. So thus z is equal to nth and the root of p we are writing here. Cos phi by n plus I sin phi by n we are taking here. The equation that is a z power n is equal to a we are taking here. In this fact, we are also satisfied n theta differs phi is given an integral multiply of 2 pi we are writing here. Therefore, we can claim that z power n is equal to a if and only r is equal to nth root of p. Theta is equal to phi by n and 2k phi by n we are writing here. So wherever k is integer, however, only the values therefore k is equal to 0, 1, 2, 3 we are taking here. n minus 1 we are taking here. So in n minus 1, give the different value of z, where k is equal to n plus 1, we get the same values of z again verify. For suppose theta 1 is equal to phi by n plus 2k1, but the condition of but is the condition of phi by n, then theta is equal to phi by n plus 2k2. Why? Because phi 1 theta by n, phi by n plus 2k1 phi by n. Theta 2 phi by n, 2k2 phi by n. So phi 3 we are writing phi by n plus 2k3 phi by n. So where 0 less than or k1 less than or equal to n minus 1, these conditions 0 less than or k2 less than or equal to n minus 2, 0 less than or k3 less than or equal to n minus 1. So all are n minus 1, but the values are changing k1, k2, k3, k4. So therefore, I am writing here, suppose 0 less than or k1 less than or n minus 1, less than or n minus 1, 0 less than or k3 less than or n minus 1. It's the values of the z, even the same values of the z. So that we are writing here phi by n plus 2k1 phi by n is equal to phi by n plus 2k2 phi by n into 2k2 phi by n plus 2 by 5. So where is the L is the large integer, there is this is in turn implies here, it implies here 2 into k1 minus k2 phi by n is equal to 2, which is impossible unless k1 k2 is equal to 0, L is equal to 0. The complete solution of the equation Zn is equal to a is given by z is equal to nth root of p cos phi by n plus k into 2 pi by n plus I sin phi by n plus k into 2 pi by n. So we are writing in place of theta, these values are writing here. In this one, k is equal to 0, 1, 2, 3, minus 1. Thus, there are n roots are complex numbers. They have same modules and their arguments are equally spaced here. The roots of the equation, Zn is equal to minus 1. Roots of it, Zn is equal to 1. Zn is equal to 1, we are taking here called nth roots of the unity, and if we denote here, w is cos 2 pi by n plus I sin 2 pi by n. So our call is expressed here 1 w omega square and omega n minus 1 we are taking. Suppose z0 is one of the solution here, wherein Zn is equal to a into a naught equal to 0. So let w be a solution of Zn is equal to 1. So therefore, w z0 is equal to n. So w power n z0 n That is 1a into n is equal to a we are writing here, we are taking that value. So the w z naught is a solution of the equation zn is equal to a. So therefore one example we have to take in here. We have to take here one example. So w z naught we are taking here. The solution of the one problem we have to check here. Problem. The solution of z power 4 I is equal, z power 4 is equal to 1 plus I. So therefore, obtain the follows 1 plus I is equal to root 2 plus cos I by cos pi by 4 plus I sin pi by 4. The fourth root of I, am taking here. Fourth root of I, fourth root of 1 plus I is 2 power 1 by 8 cos pi by 16 plus I sin pi by 16 we are taking here. So I am applying these values and 1 plus 2 power 1 by 8 I am leaving these values here. So we can write 2 power 1 by 8, that is cos pi by 16 plus k pi by 2 plus I sin pi by 16 plus k pi by 2. So therefore k is equal to 0, 1, 2, 3. So k is equal to 0, 1, 2, 3. Fine. So therefore find all the values. We can take find all next one, find all the values also we are taking here. So see here, that is another one we are taking here. Another example, find all the values here. Find all values of z for which e for z power 5 is equal to minus 32. So minus 32 is equal to 32 cos pi plus I sin pi I we are taking here. So therefore 32 cos of 5 plus 2ki, 5 plus 2ki we are writing here. So what is 32 plus 5 2ki plus this is the real part and imaginary part. I sin 5 plus 2ki we are writing here. K is equal to 0, comma plus or minus 1 plus or minus 2 we are writing. So therefore z is equal to we are writing here cos 5 plus 2k pi by 5 plus I sin 2ki by 5 we are writing here. So let's go 0, 1, 2, 3, 4. All the solutions z5 is equal to minus 32. So therefore we are approaching the values of the same. This one we are doing here. Therefore, example, to find all the solutions of z power 5 is equal to minus 32. So this one, find all the solutions. Just now we are finding this one. All the solutions of z power 4 plus z square plus 1 is equal to 0. So z power 6 minus 1 we are taking here. Consider the identity z square minus 1 into z power 4 plus z square. So z6 minus 1 we are taking this one. These multiplies this one. This z power 4 plus z square plus 1 is came in here. These values are came in here from we are thinking that one. So the solution of z power 4 plus z square plus 1 is equal to 0. Given the equation, we are writing z is equal to plus or minus 1 and z square minus 1 is equal to 0. So therefore z power 6 minus 1 is equal to 0. So z power 6 minus 1 is equal to 0 or z power 6 is equal to 1. So therefore z is equal to cos 2k pi by 6 plus I sin 2k pi by 6 we are writing here. So therefore k is equal to 0, 1, 2, 3, 4, 5 we are writing here. So but z is equal to plus or minus 1. Corresponding the values k is equal to 0, comma 3 respectively here. So solution of z power 4 plus z square plus 1. So the z power 4 plus z square plus 1 we are writing is equal to 0. So the corresponding value is equal to z is equal to 0 cos k pi by 3 and plus I said the multiplying here and so the solving here k pi by 3. So k is equal to 1, 2, 4, 1, 2, 3, 4 and 0, 3 at the 0, 3 respective taken, we are did not taking 3. So k is equal to the 0. So the 1, 2, comma 4 and 5 we are taking here. Then z value we are taking here. Therefore, one other definition we are taking here. Under definition we are z is equal to x plus iy, the number of x minus iy, for the conjugate of z, we write mod modulus of bar z of x minus iy. So we know that z bar is equal to, we know that z bar is equal to z into z bar. We know that z into z bar know that x square plus y square. So that is equal to, we write is equal to modulus of z square. So any expression we are taking here. So any expression we are taking here, a plus ib by c plus id. So where c plus id not equal to 0, we are taking here. You can simplify without sorting the polar form. You can make the denominator of the simple form. We are taking a plus ib by c plus id. So therefore, a plus ib by c plus id into, we are rationalizing c minus id by c minus id. We are rationalizing this one. So we are rationalizing this one. We have to do here. So a plus ib, c minus id. So now I am multiplying a c plus b. So this one a c plus b into I square minus 1. Then I common this b c minus id. I already told in the beginning of the class. This is c plus id. You know that c square minus c square plus d square. Why? Because I into I square minus 1. So minus into minus plus c, that is c square plus d square. You can write ac plus bd by c square plus d square plus I into BC minus AD by C square plus D square. This is the value of this one. So we have simplification of this one we are doing here. Then another, this you have to do here, and I am going to another one. Complex complex planes as a metric space we are discussing right now. Complex planes as metric space we are discussing right now. Complex plane as a metric space. Complex plane as a metric space. In this section, character together necessary metric properties of the complex plane which are required of the study. A metric space x comma d we are taking here, where x is the non-empty. This is the definition. X is the d, x the non-empty set. D is a function from the x into x. That is x into x means Cartesian product of x with x, and the R is called distance function of the metric satisfy the following condition for x, y, z in x. So therefore, dx comma y greater than or equal to 0, dx comma y is equal to 0. If and only we are writing x is equal to y, dx comma y is equal to dx, y comma x, we are writing symmetry, dx comma z is equal to less than or equal to dx comma y plus dy comma z It is a triangle inequality we are writing here. Let x is equal to c. Let x is equal to c. We are writing here, define the distance function on the d. By the rule we are writing here d z comma w. We are writing modulus of z minus w. We are writing the modules of the complex numbers. In the definition of the modules of the complex numbers, verify that d satisfies the properties of the mentioned above. Hence, we can use the c comma d, the complex number in the matrix space d. This is a matrix space here, finding here. So one definition and a problem we are taking here. One definition we are taking here. The epsilon neighborhood point z naught denoted by n epsilon z naught is a set of all points z in C, z minus z naught less than epsilon. So n epsilon z naught we are writing here, that is z belongs to C by modulus of z minus z naught less than epsilon. So n epsilon z naught means we are writing here. మేడం మనము మొదటి నుంచి వద్దని రాయొద్దు అనుకుంటున్నాం, అవే రాసాం, దాంతో క్లెయిమ్ అవుతుంది. సరే, ఒక యాక్చువల్గా ఏం జరిగిందంటే మనం అసలు మీరు ఇచ్చిందేమో హైపర్ టెన్షన్ రాశారా? ఇప్పుడు ఇప్పుడు హైపర్ టెన్షన్ రాసాం. అదే ఇప్పుడు ఒకటి సింగిల్ పేపర్ పంపిస్తున్నాను, మీరు ప్రింట్ తీసేటప్పుడు అది తీసేసి ఇది పెట్టండి. అది సింగిల్ ఇవ్వండి, ఎందుకంటే అంతకుముందు పంపిన దాంట్లోనేమో షుగర్ ఉందని రాశారు మీరు. అంతకుముందు పంపారు మీరు, అంతకుముందు 24 పేజీలు నాకు హార్డ్ కాపీ మన అప్పుడు దానిలో షుగర్ ఉందని రాశారు, ఇలా హైపర్ టెన్షన్ ఉందని రాశారు. సో హైపర్ టెన్షన్ ఒక నిమిషం. So Z belongs to see Z minus Z not epsilon. So in the geometrically we are taking here. Geometrically we are taking here. Just a minute. So see here in that geometrical way, I think n epsilon z naught we are taking here is the just disk with the center z naught missing all points. The distance less than from the point z naught comma z naught is the call of the neighborhood and is called as the radius of the neighborhood. For example, the disk z belongs to, see we are taking here z greater than 1, less than 1 neighborhood of the origin of the complex number, the center and the radius is 1. How it is 1 center and we are taking this one graph z z naught 1, this one, so y. So this is the we are taking z belongs to, C we are writing here. Then another definition of the open set. What is meaning of open set we are making here? The open set, a subset of S subset of F subset of equal to C is said to be open, and every Z naught belongs to S has a corresponding real number epsilon greater than 0. So n epsilon Z naught subset of S and is state. So the disk n belongs to the disk Z naught belongs to Z naught. So it's self open for if Z1 belongs to n belongs to Z naught, then modulus of Z minus Z naught less than epsilon. So choose delta greater than 0 such that delta greater than 0. So delta less than epsilon minus Z1 minus Z naught we are writing it. So consider n naught. So consider we are taking here. So consider we are taking here. So see here. Uh, so if delta is epsilon Z1 minus Z naught we are taking here. So consider n delta Z1 now Z2 delta epsilon Z1. So we are taking modulus of Z2 minus Z1 delta epsilon minus Z1 minus Z naught we are taking here. So Z2 minus Z1 plus Z1 minus Z naught less than epsilon. So Z2 minus Z naught that is less than epsilon we are taking here. In the condition of we are taking here Z naught of Z1. So this is the figure of this one. So in the choosing this the triangle inequality, choosing this the triangle inequality, Z2 belongs to Z0 we are taking here. So Z belongs to Z1, subset of N belongs to Z0. Seeing the figure of this one. So set the figure this one we are taking here. Just this one, the complete this is called as open set. What is the definition of closed set? Closed set. This is the closed set. What the subset is a closed set, the complete of essentially namely is set open. So another way characterizing the closed set using the motion, the limit point of the subset of it. Then limit point. What is the limit point we are taking here? So limit point we are taking here. So a complex number Z0 is a limit point of a set S every n belongs to Z0 is a contains a point of S neither Z0. In the definition, a Z0 not have be a number of S, the essential features of a line point that has point of S orbitally closer it is. For each n belongs to Z0 must contain infinitely many points of S. For if some n belongs to Z0 contains the finite numbers we are taking here, Z1, Z2, Z3, Z4, Z5, Z6, and again is distinct from Z0 by taking the small values, then Z does not contain any point of this differential. So let S is equal to I by 2, I by 3, and I by n. So this is the subset of C. The neighborhood z is equal to 0 contains z is equal to 0 is the limit of point of x. So s is equal to 0, 0, 1 meaning I. Each point of 0, 1 is a limit point, but it is not a limited point of x. Therefore, a single term set is always closure set. Not every point of the closure set needs to be limit point of the set we are taking here. So in the next class, we have to take the one definition of this one. Any doubts, ask me.